Okay, so we've established the baselines, the essentials, if you will, of talking about logarithms and seen the relationship to exponential expressions. So moving on, I wanted to take a look at some useful properties that we're going to be able to take advantage of in some scenarios we're going to see going forward. That's not a typo on my part. These really are properties 3, 4, and 5 on the notes file I'm taking for granted you're looking at as you take a look at this video. We'll get back to properties 1 and 2 eventually, but they don't really tie into what I'm wanting to talk about right now. So we're going to hop over them. The key idea here is that logarithms actually give us a way to break apart things. If you really dig into the history, that's part of why folks started using logarithms in the first place, because some math operations are easier to do by hand than others, and without fancy computing technology, tools were developed. So on the one hand, we have here m and n are a couple of positive numbers. If you have them multiplied together inside a logarithm like this, you can break it apart into two separate logarithms connected by addition. So a product becomes a sum. Similarly speaking, if you've got m divided by n, so yeah, this takes for granted, again, m and n are assumed to be positive because logarithms aren't defined for negative numbers for what we're doing. So the base A log of m over n, division, turns into subtraction. That may make sense, if you think about the connection between multiplication and division here, and then addition and subtraction are on the other side right there. So 2 properties down. The third, and in some instances I almost want to say that it's the most important one we're going to end up using going forward, is property 5 here, that if we have m raised to the nth power, so we have an exponent inside a logarithm, as it turns out, we can kind of take that exponent and he hops out front and becomes a coefficient. So we have n times the log of m. So we're going to be using these properties in some examples in just a moment. And again, I promise eventually you're going to see in particular why this guy right here is going to be really useful for us. Now I'm going to give you a brief moment to get these guys sketched down onto your notes wherever you need them. Beat. All right, let's go on. So our examples, so suppose that you're supplied with the values of the logarithms of 3 numbers, x, y, and z. So this could be any base you want. I'm just writing them as base 10 at the moment because it's actually not going to matter for what we're attempting to use them for. So the logarithm value for x is 3.1. For y, we get 1.8. Z at the back has a logarithm value of 2.7. So the idea is we don't actually know what x, y, and z are. You could rearrange to figure out what they are, but that's not quite what I'm really wanting to do here. So suppose that for some reason we needed to figure out the value of, I'm not writing a base here, let's just be consistent, the log of y times z. Property 3 that we just discussed says I can take this apart and write it as 2 logs added together. So we have log of y plus log of z. And we already know what these values for these logarithms are. We're not plugging these values in and calculating logs again. All we need to do is take the log of y, which is 1.8, the log of z, which is 2.7, and then add those 2 values together. So we're not actually having ever to press the log button on a calculator or anything like that. So that gives us an end result of 4.5. Cool. What if we had actually needed this instead? So we have the log of z divided by y. So now it's not a multiplication, it's a division. We're going to use that property to talk about division. That was property 4. So remember, it is log of numerator, the log of the top, minus the log of the denominator in the bottom. So we have the log of z minus the log of y. And we said before, the log of z is 2.7. The log of y is 1.8. We work out the arithmetic there. 2.7 minus 1.8 gives us a final value of 0.9 in that instance. All right? All right. So the last one I want to take a look at here is, again, kind of tricky, but so we have the log of the cube root of z. So I'm going to call back to something from our previous video. Again, if you need to go poke around and play around with properties of exponents to see why this ends up happening, that's fine. The magic of exponents says I can write this cube root of z that's showing up here as z raised to the 1/3 power. Now I can use property 5, the one I said was super useful. I can pull that 1/3 out front of the log as a coefficient. So I'd have 1/3 times the log of z, and again, we know what that number is. It's 2.7. So we have 1/3 times our 2.7. As it turns out, that looks familiar. That really is just a coincidence in this case, based on the numbers that are chosen. That's not some like deep observation here, but we end up getting 0.9 again in this instance. So there's some examples of using these logarithmic properties, what you might call expanding logarithms, taking a big logarithmic expression in some sense and breaking it apart into smaller ones so you can work with it chunk by chunk. So that's one direction we might take this. On the other hand, we might actually have a bunch of logarithmic expressions that we need to take apart and turn into just one single logarithm. You might call that as condensing or collapsing the logarithms back together. I guess I should do it like that, but you get the idea. So, wanted to take a look at an example of that in action. So, this instance, I'll write the logs this time. It's not strictly necessary. So we have 2 times the base 5 log of x plus 1 minus the log base 5 of the expression 3x plus 2. So what I'm going to do here is use those properties of logarithms kind of in reverse. So I'll still flag out which property I'm using, but it's actually kind of traveling in the opposite direction from what we just did with the x, y, z numerical examples we just took a look at. So first off, I've got a coefficient of 2 sitting in front of this one logarithm here. So I'm going to use property 5 sort of in reverse and vacuum that guy back up in here as an exponent. So yeah, that's property 5 going in the opposite direction. So we have the log base 5 of x plus 1 quantity squared. You don't really need to be quite this careful with this. I just like to do it to make sure I know that that square is actually inside the logarithm. That's why I've got that second set of brackets there. It's not representing a matrix or anything. And then we have still the base 5 log of 3x plus 2 sitting in the back. I do want to point out this stage, it's going to be important for what we do next, that these bases do in fact match. If this were a base 5 log, and this were like a base 3 log or a natural log or something like that, we're not going to be able to do what comes next. The exponent thing is still hunky-dory though. So now we have 2 logarithms linked together with a subtraction. And using property 4, a subtraction on the outside is going to turn into a division on the inside. That's right. So we'll have the thing in front is going to be on the top of the fraction, so this x plus 1 squared divided by 3x plus 2. So you might not write that extra set of parentheses. I like to do it just from my background. I'm used to enclosing arguments of things like logarithms and parentheses. So again, it's not strictly necessary, but it does make sure you're 100% clear on exactly how things are being grouped up. So that's some properties of exponents. So I do want to take a look at at one other type of formula, how we can use it in an application, and then we're going to come back and revisit those 2 properties that I kind of hopped over. It's going to make for a good bridge as we move into our next section of material. So That's where we're headed. Stay tuned.